First two questions. So exhausted after your weekend, aren't you?
I was doing so much yesterday. I wanted to go home.
Answering these questions in the chat. All right, so this would imply that we have to remember the definition to a convex polygon. There's a difference between a concave polygon and a convex polygon. What does a convex polygon do? There's at least one vertex that dips into the interior of the polygon, whereas I said that totally backwards. Convex, it would be that all vertices would be pushed out. It'd be like you being inside the polygon, and you're pushing on every single vertex out. Whereas concave, one of the vertices is caved in, like this one. See how that's caved into the middle? So that one right there is your concave. So they want you to cross out on number 2 the polygon that is not convex. So this is convex, everything's pushed out, that's convex, and that's convex. This is the one that is concave. And so in a convex polygon, no point on the lines containing the sides of the polygon is in the interior of the polygon. So if I took a straight edge along each of these convex polygons and I put my straight edge along the outside edge, notice that it does not go through the middle of that polygon, no matter which edge that I put this on. Whereas on the concave one, if I put my ruler here, notice that this part, if I extend that side, is in the interior of that polygon. So that's what they're looking for. And then we do have a new vocabulary word because our entire chapter is really going to be dealing with quadrilaterals, but we're going to start off today with specifically polygons in general. And a regular polygon, emphasis on the word regular, is a polygon that is both equilateral and equiangular. So that means that all angles are congruent and all sides are congruent. And that's what the word regular is telling you. So if you have a regular pentagon, they're telling you all interior angles are congruent and all exterior sides are congruent. So then look at 4 through 5, or 3 through 5. The sides of a regular polygon are what? Based on what I just told you, sides of a regular polygon are congruent. A right triangle. Do you think a right triangle is a regular polygon or is not? Can it be or can it not be? Let's think about a right triangle. I'm going to make an isosceles right triangle. There's an isosceles right triangle. Can the hypotenuse be equal to those sides? No? Why? The hypotenuse is always the longest side of the triangle. So it is impossible for all 3 sides to be equal on a right triangle. It's impossible. At most, you can have 2 sides equal, in this case, an isosceles right triangle. So your answer to this one is not a regular polygon. What kind of a triangle is a regular polygon? Equilateral. Remember the name for an equilateral triangle, the technical name that has a first name and a last name is equiangular equilateral. But we don't ever call an equilateral triangle equiangular equilateral, it's not that. So an isosceles triangle is or is not always a regular polygon. So let's look at an isosceles triangle that's not right. Because here's an example of where it is not a regular polygon, correct? Alright, so I'm off this maybe, but let's just assume for chuckle's sake. There's my isosceles triangle. Could I have an isosceles triangle that is a regular polygon? How? That's an equilateral triangle. Is an equilateral triangle also an isosceles triangle? The definition of an isosceles triangle is that it has at least two sides that are equal, and an equilateral triangle matches that. So an equilateral triangle is an isosceles triangle that is special. And so if an isosceles triangle is equilateral, then it will be a regular polygon, but didn't I also prove here that it doesn't have to be by an isosceles right triangle? So the answer to this one would be what? It's not always. It's sometimes, but not always. So only when it's an equilateral would it be a regular polygon. So then on these 3, 6, 7, 8, I want you to determine if it's just equiangular, just equilateral, or both, meaning it's regular. Because if it's both equiangular and equilateral, then it's a regular polygon. So you put on there which one you think it is. And then share with those around you what you think they are. So share with at least 1 to 2 people around you. Everybody share. So in Tori talk, Madeline, and Alma talk. Justin and Skylar talk. She's into her double negatives today. She's quite proud of it.
She's quite sassy today, too. She's like, it's my birthday tomorrow. I'm not going to get down for
Is it
anything.
your birthday tomorrow?
Yes.
Happy birthday. Are we going to be 16?
Yes.
You're going to be driving?
Yes. Brody, you're so mean.
What did he just say?
He thinks I'm sick.
Oh. Because she's tiny.
Yeah, pretty much.
That just means, Bailey, you're always going to look young, which is always a good thing. All right, so here are your answers. Here are your answers. So 6, Ishak, Bailey, 6 is equilateral because all you can assume is that the sides are equal because they're all equally tick marked. And obviously, these angles are not the same as these angles. These are acute angles and these are obtuse angles. So it can't be equal angular as well. This one in the middle, you're told that every single angle is 120 degrees. How else could they have told you that every single angle was the same? Arc marks. Yeah. Bless you. Bless you. And then since they've marked every side as well with a single tick mark, it is both equiangular and equilateral, so therefore it matches the definition of regular. And then number 8, visually, these sides are not the same as these sides. And so it is only equiangular. All right, so flip that. We come to our first theorem and corollary. Really, I don't believe you've had a corollary yet. That's not a coronary, like a heart attack. Corollary. But it could give you a heart attack if you don't learn it, right?
Bless you, Brenner.
All right, so theorem 6.1 says that the sum of the measures of the interior angles of an n-gon, n representing the number of sides of that polygon, so a triangle, quadrilateral, pentagon, hexagon, so forth, is very specifically n minus 2 times 180. So the number of sides of that quadrilateral minus 2, whatever that amount is, times 180 degrees. And I'll show you why this is in a minute. Then we have a corollary that says the measure of each interior angle, one interior angle. So this is the measure of all of the interior angles. So this is the measure of all of the interior angles. You might want to put up here all. Whereas this is the measure of one interior angle. So this is just one. And it looks very similar. The only difference is you take that amount that you got for all the angles and you divide it by n. Why divide it by the number of sides? If you look at a polygon, so look at this one here. How many sides does this have? 6. And how many angles does it have? Vertices, 6. So whatever the number of sides are that any polygon has, it's going to have the same number of angles. So if I find the sum of the measures of all of the interior angles inside the polygon and I divide it by the number of sides, that's going to give me the measure of one angle, one specific angle. And so that's what they're doing there. So when n minus 2 is equal to 1, so the number of sides of a polygon minus 2 is equal to 1, the polygon must be A or n. Is it a hexagon, decagon, pentagon? No, a circle is not a polygon. Why is a circle not a polygon? It has to be made up of straight sides and it has to be closed. So it can be a circle. It is a triangle. A triangle has how many sides? No. How many sides does a triangle have? How many sides does a triangle have? 3. Thank you. So it's got 3 sides minus 2 is equal to 1. So when n minus 2 is equal to 2, what do we have? What's the proper word? Because a square is not the only type of
polygon quadrilateral.
There you go. So we're going to say, you cannot say it's a square because we don't know that all sides are equal on this. You cannot say it's a rectangle because we don't know that it has 4 right angles and 2 pairs of congruent sides. You have to call it a quadrilateral. That is its general term. And so then quadrilateral has 4 sides minus 2 equals 2.
And the number of sides.
N is the number of sides. So let me just take your quadrilateral and explain something to you. So we're going to take something small. So let's draw a rectangle. Or something close to a rectangle. So here's my rectangle. How many diagonals can I draw from one vertex and one vertex only? And a diagonal must go through the middle of the polygon and cannot be one of the sides of a polygon. Ladies, what's going on? Do you have a question or no? So how many, let's just take this vertex right here. How many diagonals can I draw to another vertex from that one? Just one. That's the only diagonal I can draw. Agreed? Do you see how there are triangles created within there? How many triangles? 1, 2. So if I took the number of sides of this rectangle, 4, and I put it up here, what's 4 minus 2? 2 times 180. 360 degrees. So if I take one triangle, two triangles, what are the sum of the angles inside the triangle? 180. What's 180 times 2? This is where the n minus 2 comes from because this is calculating the number of triangles that are created by the diagonals from one vertex. And we just multiply it by 180. And we know that a rectangle has what angles here?
Right.
Right, so it's 90 degrees. What's 90 times 4? He's on a roll today. 360 degrees. So I took a figure that you're familiar with, and I made a diagonal in it. Now, if you look at a triangle, can I make a diagonal in a triangle? So, can I draw a diagonal from this vertex to another vertex? No. So, if you use a triangle, 3 minus 2 would be right here equals 1. It's just 1 times 180 because a triangle is a triangle. It has 180 degrees. You cannot draw a diagonal through a triangle. That is the one polygon that you cannot draw diagonals through. Any other polygon you can. So then we're going to look at a much larger polygon. This is kind of a bad picture because it's kind of hard to tell, but you also have a vertex here, so put a dot here, very hard to see, and you have a vertex here. So what I want you to do is take vertex A, and vertex A is right here. And I want you to take a straight edge. It's imperative that you use a straight edge. And this is a 17agon. After decagon, we don't really use the proper names for the sides of the polygon. I'm only going to require you to know up to 10. Those are the most popular. 12 is used often, but you probably won't be tested on. Anybody know what 12 would be? No, the proper word for 12. I love this word. It sounds like that is very good.
Good job.
All right, so yes, 12 is dodecagon. So that might be an extra credit question. All right, so let's take from A, we're going to draw a diagonal. So I can't draw a diagonal from here to here because that is a side, but I can draw a diagonal from here to here, so it's very narrow. And if you don't use a straight edge, it's going to be hard to get them to look correct. And you can actually draw some really beautiful pictures using diagonals in polygons. Like a string design. So if there's 17 sides, how many triangles theoretically should we have? Nope, 17 sides, how many triangles should we have? 15. How do you get that? Yep, 17 minus 2 should give you the number of triangles. So then if you number your triangles, this one's really hard to see, this one's really tiny, this is 1. So I did squeeze 15 triangles in there. That upper one by A is really hard to see, but it's there. So, once you get there, we're going to fill out the information to the left. So you know that thing hanging around your neck is a perfect straight edge, right? Alright, so we're going to use the polygon angle-sum theorem, polygon angle-sum theorem. I don't even really call that, I just call it the sum angle theorem for polygon. I'm not going to test you on knowing that, but you need to know if I happen to say that, what that means. So that would imply that we have an n here. And then what are we going to substitute in for n? Because they're telling you to substitute in for n. What are we subbing? We're subbing in 17. 17 minus 2 is 15, and that's the number of triangles that we got. And then I want you to take 15 and multiply it by 180. Mariah? Did she need to take her stuff with her? Yep, grab all your stuff here. Just watch the video. Pardon? This one is 17, yes. And we got that because we have a 17 gone. 17 gone. I'm used to calling it a gone from another text. Anybody have 15 times 180 yet? What'd you get? No, almost. You're off by a bit. You made a mistake. Did you use your calculator?
Yeah.
Let's try it again. 3,700?
27.
Yeah, but he said, oh, I thought you said 3,700. Yeah, you're correct. Like, you used your calculator, you got that? Like, looking at my calculation. Alright, so the sum of all the interior angle measures of a 17 gone, and notice that they're not saying that this is a regular polygon. This works for regular and non-regular, is 2,700 degrees. Now, if this were a regular 17 gone, if it were a regular 17 gone, regular 17 gone, the measure of one angle is, take that 2,700 that we just came up with and divide it by how many sides? 17. So if you would please do that for me. What do we get? Exactly. Okay. So 158 point, and what follows it to? A what? Okay, so 82 degrees. So if it were regular 17 gone, then we would take that sum and divide it amongst 17 angles, and we would have about 158.82 degrees. So you have to pay attention on your homework as to what they're asking you to find. Are they asking you to find all the angles, or are they asking you to find one interior angle? Is it a regular polygon? If this were not a regular polygon like this one isn't, I wouldn't be able to tell what each angle is individually. I can only tell what they all are together. But the minute it's a regular polygon, then I can take that information and divide it by the number of angles or sides, either one, and get that interior angle. So then look at 14 through 17. What is the measure of each interior angle in a regular nonagon? Well, it'd be handy if we wrote out all the different names for our polygons over here. So our smallest polygon is a what? Smallest polygon. Triangle. So a triangle has 3 sides. Then we just discussed a quadrilateral is 4 sides. Then what is 5 sides? Pentagon. 6 sides, what's that? Nope. 6 sides. It's not a septagon, hexagon. And if you don't know these, you need to put them on flashcards and learn them. What is 7 sides? There are 2 different words for 7 sides. You can either use heptagon or septagon. Both of those mean 7 sides. So know both of them. I don't know which one you might come across. And then 8 sides, which is can't call it a stop sign. So octagon. But you are right, that is a stop sign. 8. And then what's 9? Nonagon is equal to 9. And then what did we say 10 was? Deca with a C. Decagon equals 10. And your extra credit question would be, what's 12 sides? Dodecagon. Sounds like a dodo bird. An extinct animal, dodecadon. D-O-D-E-C-A. Geo Lesson. So this one just might be an extra credit question. an 11-gon. But because dodecagon is used often, then I like you to know. Okay, so the fact that they're telling you that you have a regular nonagon, you need to make that connection that this is a 9-sided figure. So when they name that, 9 sides. So that tells me that all of my interior angles are the same, all of my exterior sides are the same, and I have 9 sides. So the interior angles in a regular polygon, are they congruent or different? They are congruent. A nonagon, we just said, has 9 sides. So we're going to use the sum angle theorem to find the measure of one angle. So we're going to take our 9 minus 2 and divide it by 9, which gives us 7 times 180 divided by 9. So what's 7 times 180? And if you want to use a calculator for this homework, so long as you're writing this part out and just don't give me an answer, you're welcome to use a calculator. But if you're going to just go from the question to the answer, I'm not going to give you credit for it. So you have to show me what you're putting into the calculator and then what comes out. So what do we get? Somebody do it. I already know the answer, so somebody do it. Divide by 9. When you divide by 9, what do you get? Okay. So we get 140 degrees, so that means that the measure of just one angle is 140. But 7 times 180, the sum of all angles equals 1260, right? Is that what you told me, Bailey? Yep. So know the difference between what they're asking and what you're finding. So this particular question, they could have asked either one. All right, so flip it. Look at problem 3. It says, what is the measure of angle G in quadrilateral EFGH? Is that a regular polygon? No. And at this point, you should kind of already know what the angles are supposed to add up to in a quadrilateral because it's one we've used often. You can always think of that rectangle. But we're going to go through our sum angle theorem anyway. And so for this one, we take the measure of all of the angles and add them together. We know 3 of them. I'm going to let this one be x. If I don't know it, I'm going to let it be x. And so the measure of all the angles added together, all 4, should equal 4 sides minus 2 times 180. Our 4 sides minus 2 is 2. 2 times 180 is 360 degrees. So then let's look at the left side. So the left side, what is the measure of angle E? 85. F? 120. G, we don't know, so we're letting it be x. And H is 53. So if I add up, and they're calling my x angle G, so if I add up these 3 angles, what do I get? $258. And then how are you going to solve? 360 minus 258, what do you get? $102 degrees. Does this look like it could be a 102 degree angle? Does it look obtuse? Yep, and so you want to check those. Even though you can't take a protractor to this and check it, because you're probably going to be off, you can at least determine if it looks to be obtuse, you should have an obtuse angle measure. If it looks to be acute, you should have an acute angle measure. So you can use those as checks. So the measure of angle G in quadrilateral EFGH is 102 degrees. Then we have another theorem, which is a really handy theorem, and your textbook kind of gives you the harder way to find it. So I'm going to talk to you about using the easier method. And there's an easier method to finding your interior angle using this theorem rather than this one here. So there's a much easier way. So we're going to come back to this, and you're going to write in here there's an easier method. Okay? So, but we'll come back to it after we look at this. So this theorem says the sum of the measures of all the exterior angles of a polygon, one at each vertex, is 360 degrees. Well, what does the exterior angle look like? Look at just one side here. There's one side that makes a straight line. And so isn't there an angle here and an angle in here? What do you know about, this is the interior angle, and this right here, angle number 2, that's the exterior angle. So all you have to do is extend the sides of your polygon to create those exterior angles. It kind of looks like a pinwheel, doesn't it? And so you want to keep extending the sides in the correct direction, and so these sides are being extended counterclockwise. But if you notice that one interior angle and one exterior angle add up to give you what? 180 degrees. So the interior angle plus the exterior angle equals 180 degrees. And it doesn't matter whether that polygon is regular or not. What's going to happen no matter what. And because I can actually take this and see if I can find its center. Not letting me. Let's try this. Okay, my first one is students. Head just did. Yeah, I made a circle. That circle is circumscribed, and what is happening at each vertex? What's happening at each vertex? They're doing what? They're hitting my circle, right? So essentially what's happening is if I were to create with each of these angles in here, they all make 180 degrees. And the reason why these exterior angles make 180 degrees is because of that circle can be, this happens to be a regular polygon, but you can circumscribe a circle around there. So think in terms of I'm going all the way around, it's always 180 degrees. This is how many sides here. How many sides does this have? 5. How many sides does this have? 4. Doesn't matter even with a triangle. Think in terms of a triangle. So if I took my triangle that I drew over here, and let's extend the sides. So let's extend this side. Let's extend this side. And let's extend this side. And let's just pretend for chuckle's sake that I have an equilateral triangle. Wouldn't this be 60, 60, 60? And if that's 60, what's this one? If that's 60, what's this one? 120. So that means that this one here is 120. And this one here is 120. What's 120 times 3? 360. So it doesn't matter if it's a triangle, or if it's a pentagon, or even a quadrilateral. If you add these up, let's go ahead and find those. So let's look at 120 plus 81 plus 72 plus 87. Somebody add those up and double check that they do add to 360. Ian, did it? Yep. What was that? So it shouldn't matter. Now add all these up. Add all these up. Let's see what they add up to. Yep, that equals 360 as well. So what they could do is they could give you all of the angles, and let's say they left that one blank. And you notice that all the angles are exterior angles. You can take 360 degrees and subtract the sum of the angles you have to get what's left over. And so here, that's what they're doing here essentially. They're showing you that, oh, okay, exterior angles add up to 360. If I didn't know the 72, I would just add those three and subtract them. What's left over must be the angle measure. So let's look at 23 through 27. Since the nonagon is regular, its interior angles are what? Since the nonagon is regular, and this is what they're referring to. What is the measure of an exterior angle of a regular nonagon? And this is what I'm going to get to, the shorter way. Now they're going to teach you the longer way. I'm going to show you the shorter way. So they tell you it's a regular nonagon. So because it's regular, what do you know about the interior angles? Congruent or right? They're congruent. The exterior angles are complements or supplements of the interior angles. They go alphabetically and numerically in order. 90 comes before 180, and complementary comes before supplementary, so 90 lines up with complement, and 180 lines up with supplement. So which is it? They are supplementary. Since the nonagon is regular, its exterior angles are congruent or right. They are also congruent. It's regular. And then the sum of the measures of the exterior angles of a polygon is always what? Always 360. It doesn't matter. Notice that they said polygon. It doesn't matter if I said triangle, quadrilateral, pentagon, hexagon. They are all 360 degrees, and you will miss this problem. You will miss this question. 85% of you are going to miss that question because you don't study it. So you might want to star it and study it, because I'm telling you, you're going to miss that question. What are the sum of the measures of the exterior angles of a heptagon? 360. What are the sum of the measures of the exterior angles of a dodecagon? 360. It's always the same. All right, so then 27, a regular nonagon has how many sides? 9. So don't flip it yet. Let's talk about this. So what they want you to do, this is what they want you to do. They want you to take the sum angle theorem and find all the sum. Well, what would be the quick way to do this? You could find the sum of all of the interior angles, right? So 9 minus 2 times 180 divided by 9. And then you could divide that, divided by 9 is going to give you the one interior angle. And you could take that, you could subtract it from 180 to get one exterior angle. But what's a quicker way? The sum of the measures of the exterior angles is 360. What's a quicker way? Can't you just take 360 degrees and divide it by what? 9 sides? And what does that give you? How many times does 9 go into 36? 9 goes into 36 4 times. 9 goes into 0? 0 times. So that is equal to one exterior angle. That's the quick way. If it's a regular polygon. If it's not, and furthermore, if I ask you to find the measure of one interior angle, I very rarely use the sum angle theorem to find an interior angle. Because if my exterior angle is 40 degrees, what's my interior angle? Won't my interior angle be 140 degrees? How do I find that without taking 9 minus 2 times 180 and divide that by 9? I certainly didn't do that in my head. These are supposed to be supplementary, right? So the quickest way to find an interior angle of a regular polygon is to use the exterior angle theorem. Find the exterior angle first, and then find the interior angle. Your book will tell you to use this interior angle theorem right here. The book will tell you to use this. But if it's a regular polygon, use the exterior angle theorem first. So 360 divided by n. And that could be your number of sides or your number of vertices. It's interchangeable, it won't matter. And so if I find the exterior angle first, then you can find the interior angle. And so now look at the very back of the sheet. And we're going to write the shortened way on the back of the sheet. So back here, what is the measure of an exterior angle of a regular monogon? So it is, as we just stated, 40 degrees. And we got that by taking 360 degrees and dividing it by 9. And so in words, take 360 degrees and divide by the number of sides. And in this case, the number of sides was 1. So the last thing that we're going to do is the lesson check. So error analysis. Your friend says that she measured an interior angle of a regular polygon. It's important that you note that they mentioned it's a regular polygon. What do you know about regular polygons? All interior, all exterior, all sides are equal. And so he or she found it to be 130 degrees. So it's an interior angle was 130 degrees. And you want to explain why this result is impossible. So it's a little funky to try to follow their logic here. But they're going to use indirect reasoning to find a contradiction. In other words, to prove that it's wrong. So assume temporarily that a regular n-gon has a 130 degree interior angle. So we're just going to assume that this person is correct. The sum angle theorem says a regular n-gon has n congruent sides. So we don't know how many sides this thing has, right? But if we did know the number of sides, to find the total angles on the inside of the polygon, wouldn't you take 130 degrees, each interior angle, and multiply it by the number of sides? Would that give us the total amount that the interior angles add up to? So the sum angle theorem, the polygon angle sum theorem, says you take the number of sides and subtract it by 2, and that equals 180 degrees. So theoretically, these two should be equal, shouldn't they? If I took n minus 2, it should be exactly equal to the 130 times n. If I multiply those together, I get 130 times n. So now they want you to use a distributive property here. So 180 times n is 180n. 180 times a negative 2 is a negative 360. And that should still equal 130n. So now what do you do? They want you to subtract the 130n from both sides. So you already get a negative. If I subtract 180 from both sides, what do I get on the left? Well, 180 minus 130 is 50, and because the 180 is negative, it's a negative 50n. That should equal a negative 360. Then we're going to divide this side by negative 50 and this side by negative 50. Somebody do that on their calculator, please. What's negative 360 divided by negative 50? You get a positive, what? 7.2. What does n represent? What does n represent? The number of sides, or the number of vertices. Can you have the number of sides be 7.2 sides? No. So n cannot be 7.2, and here's why. The number of sides in this case n must be a whole number greater than or equal to what number? What's the smallest number of sides you can have on a polygon? 3. So it has to be greater than or equal to 3. And although 7.2 is greater than or equal to 3, it is not a whole number. Whole numbers are 0, 1, 2, 3, 4, and so forth. So it's not a whole number greater than or equal to 3.